let's apply some more ratio and root tests here. I've got 1 over n to the n. So when I have 1 over n to the n, I have something to the nth power. If everything there is to the nth power, it is a great candidate for the root test. So all I have to do for the root test is say, okay, well, a sub n is 1 over n to the n, which we can write as n to the negative n. And so I can also take an absolute value there. So I have to take the nth root of this absolute value. Now what we know is that the root can be written as a fraction. And say, well, that's limit as n goes to infinity, n to the n to the 1 over n. And by the power of or the properties of exponents, since I have this thing to power raised to another power, I can write that as a product of the powers. Well, n times 1 over n is just going to be 1, and then of course you have the negative. So I have the limit as n goes to infinity of n to the negative 1, which is 1 over n. So then this limit goes to 0. Well, the root test says as long as that limit is less than 1. It could be 1/2, but 0 is clearly less than 1. And that limit will always be positive because of this magnitude. This is a positive value. You wouldn't end up with a negative limit. If you end up with a negative value of a limit when you're doing this, you've definitely done something wrong. So that tells us that this is not just convergent, but it is absolutely convergent. You also could have done this by like a direct comparison. You'll notice that, specifically for n is 3 and beyond, this is going to be less than a 1 over 3 to the n, which is a geometric series. So, just thoughts there. Now, for this one, we have factorials. So, when we're dealing with factorials, usually we want to use the ratio test. Not always, but usually. So, I have a sub n So how do we get a sub n plus 1 here? To get a sub n plus 1, of course I get negative 1 to the n plus 1, n plus 1 factorial. But what does that denominator look like? Well, if we have all those terms, because we keep multiplying them together, so what we're going to get is one additional term. We're going to get everything we have here. But then you're also going to get that with an n plus 1. So you're going to get this 2n plus 1 plus 3. Now, we'd really rather write that as not this. So we're going to end up writing 2n plus 5. I also want to do a little bit of reshaping that. So when I do this, I'm going to rewrite this n plus 1 factorial more conveniently. I'm going to say that's negative 1 to the n plus 1 times n plus 1 times n factorial all over 3, 5, 7, 2n plus 3, 2n plus 5. And that's all over negative 1 to the n factorial 3, 5, 7, 2n plus 3. Of course, fractions on top of fractions is not great, so we're going to end up multiplying by the reciprocal of the denominator, giving us negative 1 to the n plus 1 plus 1 n factorial 3, 5, 7, 2n plus 3, 2n plus 5 times 3, 5, 7, 2n plus 3. You probably can't see that at all. That is a 2n plus 3. All over negative 1 to the n factorial. Okay, so sorry, I apologize for my small writing there. What we're going to have is pretty much cancellation across the board. Another thing we're going to have is these negative ones are going to go away, right? We're taking an absolute value. So after all the cancellation said and done, it doesn't matter if it's negative or positive because the absolute value just absorbs it. So what we're going to end up with here, n factorials cancel. Everything all the way to 2n plus 3 cancels. So I end up with n plus 1 over 2n plus 5. So when I take this limit, I get 1/2. So by taking that limit there, I get 1/2. Well, the ratio test says as long as that limit is less than 1, it converges. In fact, absolutely converges. So that tells me that this particular series is going to be convergent. And again, if you've studied like order of growth problems, this should have been reasonable to you, because this right here is actually 2n plus 3 factorial. So if you have an n factorial on top, but you have a 2n plus 3, that means every time n goes up, this thing really starts to outpace this thing. Like just runs way, 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 way ahead with it. So since it's running so far ahead, you can't basically you can't chase it back. Actually, this isn't. I take that back. This is not 2n plus 3 factorial. It's something kind of like 2n plus 3 factorial because you're actually skipping by 2. So you end up with like 2n plus 3, but you end up with dividing or whatever. But it works a lot like 2n plus 3 factorial, but it's going to run way, way faster ahead than n factorial. And it's going to, well, I say it's going to run about twice as fast, actually. I kind of retract what I'm saying here because for each term in n, this is going to be a 2n plus 3, so each time it keeps adding on. It's adding on about twice as much on bottom, so it's going to start to drive it down. This is going to resemble a geometric series that looks kind of like a 1 over 2 to the n.